sequence and series. In this lecture, we shall explore more on arithmetic mean and geometric mean of the numbers. Further, we will try to tackle certain problems on arithmetic progression and geometric progression. Recall that given two numbers A and B, arithmetic mean, AM for short, of A and B is defined by given two positive numbers A and B, the geometric mean of A comma B is defined as follows. Positive square root of the product AB. Let us see a few instances. Arithmetic mean of the numbers 1 and 2 is 1 plus 2 divided by 2, which is 1.5, and geometric mean of 1 and 2 is square root of 2. Arithmetic mean of 1 and 4 is 1 plus 4 by 2, which is 2.5, and geometric mean of the numbers 1 and 4 is positive square root of 4, which is 2. Arithmetic mean of 2 and 8 is 2 plus 8 by 2, which is 5, and geometric mean between 2 and 8 is 4. You can play with more numbers. From these instances, can you compare the value AM and GM of two numbers, in the sense which one is larger? You can observe that at least in this instance, arithmetic mean is greater than or equal to the geometric mean. In these cases, strictly greater than. Can we dream this inequality in general case? That is it true that arithmetic mean between two positive real numbers is always greater than or equal to geometric mean? We shall settle this question next. Let A and B be two positive real numbers. Then AM, the arithmetic mean, is A plus B by 2, and GM is root AB. We shall ask the question whether AM is always greater than or equal to Gm? Is it the case that Am greater than or equal to Gm? That is, we would like to know whether a plus b by 2 is greater than or equal to root ab. That is the question. It amounts to see if the difference Am minus Gm is non-negative. So, let us consider the difference. Consider a plus b by 2 minus root ab. With a simple manipulation, it is a plus b minus 2 times root ab by 2. Completing the numerator into square, you can observe that the numerator is root a minus root b the whole square by 2. Thus, the difference Am minus Gm is equal to root a minus root b the whole square divided by 2. Note that root a and root b are real numbers. Their difference is a real number, and square of a real number is always non-negative. Therefore, root a minus root b the whole square is non-negative, which says that the difference Am minus Gm is non-negative. Therefore, Am is greater than or equal to Gm. A plus b by 2 is greater than or equal to root ab. Thus, we established a general inequality, Am-Gm inequality, which says that arithmetic mean of two positive numbers is always greater than or equal to geometric mean between them. One may ask the question, when equality holds? Let us go back to our investigation. Am equal to Gm, then the difference is 0. So, the question reduces to when root a minus root b the whole square coincides with 0, and answer is that's when root a equal to root b. Since we deal with positive numbers, it's equivalent to say a equal to b. Thus, the observation is that equality holds if and only if a equal to b. To conclude, arithmetic mean between two numbers is always greater than or equal to geometric mean between them. Further, the arithmetic mean and geometric mean coincides only when the two numbers are equal. Let us try to interpret this arithmetic geometric mean relation geometrically. Consider a rectangle with side length A and B. Then perimeter of the rectangle will be sum of all sides, which is 2a plus 2b, and area is AB. Now, let us consider a square with area equal to area of this rectangle. Means we would like to have a square with area AB. Note that for a square, formula for area is square of the side. Therefore, to have a square with area AB, we need square of all side length root AB. Let us consider square of side lengths root AB. Then area of this square obviously is AB and perimeter is 4 times root AB, sum of lengths of all sides. Keep this in mind. Let us apply AMGM inequality to the numbers representing the side length A and B. AMGM inequality says that A plus B by 2 is greater than or equal to root AB, which is equivalent to say 2 times A plus 2 times B is greater than or equal to 4 times root AB by multiplying with 4 on both sides. Thus, interpreting AMGM inequality in terms of perimeter, we observe that among all rectangles with equal area, the perimeter of the square is the least compared to perimeter of any other rectangle having the same area. Recall, the right hand side of this inequality is perimeter of the square, and left hand side of this inequality represents perimeter of a rectangle. So, AMGM inequality immediately translates to a geometrical fact, namely among all rectangles with equal area, the square has least perimeter. Next, let me make a remark. Arithmetic mean and geometric mean we have defined for two positive real numbers. We can generalize this and define arithmetic mean and geometric mean for finite number of real numbers. To be precise, given n real numbers, A1, A2, etc. An, the arithmetic mean of these numbers is defined as AM of A1, A2, etc. An is equal to A1 plus A2 plus etc. plus An by n. we add all the numbers and divide by number of real numbers we have. Similarly, given n positive reals, a1, a2, so on, an, the geometric mean of these numbers is defined as follows: gm of a1, a2, etc. an is equal to the product a1, a2, a3, etc. an power 1 by n. Nth root of the product of the numbers. Observe that when n is equal to 2, it reduces to the formula that we had for geometric mean between two numbers. Let me mention without proof that the AM-GM inequality holds for a set of n positive reals. That is, given n positive reals, a1, a2 and so on an, the arithmetic mean of these n numbers is always greater than or equal to the geometric mean. It will be a nice exercise to establish this inequality. Note that we have this inequality in the case of two real numbers, positive real numbers, which emerged out of a very trivial fact that square of any real number is greater than or equal to 0. Using the AM-GM inequality for two real numbers as a basis and applying induction, one may try to establish it for n positive reals. Next, let us go back to an infinite series. As I told in the previous lectures, unlike a finite sum, an infinite sum or an infinite series cannot be dealt in a straightforward manner. What we do is we find sequence of partial sums. Next, we observe what happens to the sequence of partial sum as n becomes larger and larger. If the sequence of partial sum comes close to a fixed real number as n becomes larger and larger, we say the series is summable or convergent. And that fixed number to which sequence of partial sum comes close will be treated as sum of the series. In that context, we observe that a geometric series, infinite geometric series, is summable if the common ratio lies between -1 and 1, both excluded. Further, In the case of convergent, the sum has a formula given by a by 1 minus r. In the other cases, namely modulus of common ratio greater than or equal to 1, the geometric series diverges. One may ask, similar to an infinite geometric series, why don't we consider an infinite arithmetic series? That is, given an arithmetic progression a plus d, a plus 2d, so on, a plus n minus 1d, so on, can we talk about the sum n is equal to 1 to infinity a plus n minus 1d? Can we talk about sum of all terms of an arithmetic progression? Whether this series is summable. To answer this, first let us have the following observation. Let summation n is equal to 1 to infinity, an infinite series a1 plus a2 plus a3 plus so on, be convergent, meaning roughly you can add all these terms and end up with a finite value. In such case, you know that the corresponding sequence of partial sum, that is sequence of partial sum namely Sn equal to a1 plus a2 plus etc. plus an is convergent. That is, as n becomes larger and larger, the sequence of partial sum becomes sufficiently close to a fixed number, let us call it S. Thus, with the assumption that given series is summable or convergent, we have the corresponding sequence of partial sum is convergent. This should give you that as n becomes larger and larger, both Sn and Sn minus 1 are close to S. Remember, when n is large, there is no big difference between n minus 1 and n. And what we mean by convergence of a sequence is that as we progress towards the end of the sequence, all the terms get stagnated near a fixed number S. Therefore, once Sn is convergent to S, both Sn and Sn minus 1 will be very close to this fixed S when n is large. Note that Sn is sum of first n terms a1 plus a2 plus etc. plus an. Therefore, an is Sn minus Sn minus 1. Nth term is same as difference between nth term and n minus 1th term of the sequence of partial sum. Note that both Sn and Sn minus 1 are close to S when n becomes large. Hence, intuitively it should be clear that limit n tending to infinity a n is 0. As both Sn and Sn minus 1 are close to S, the difference will be close to 0 when n becomes larger. Let us not enter into the precise definition of limit of sequence and so on, but have an intuitive feeling that when Sn and Sn minus 1 are close to S, the difference will be close to 0. Therefore, limit n tending to infinity a n is 0. So, what do we have? We started with the fact that the infinite series is convergent. That infinite series finally represent a finite real number. A1 plus A2 plus A3 plus etc. amounts to some S. In that case, we conclude that the terms a n should become close to 0. Thus, summation a n is convergent implies a n tends to 0 as n tending to infinity. Recall that if you have a statement P implies Q, it is logically equivalent to not Q implies not P. Be careful, P implies Q is logically equivalent to not Q implies not P. Going back to our observation, series summation a n is convergent implies the terms becomes close to 0 as n becomes larger and larger. Hence, applying this logical equivalence, one should be able to observe that if nth term does not tend to 0 as n becomes larger and larger, we cannot expect that the corresponding series is convergent. If a n does not come close to 0 as n tending to infinity, then summation a n is not convergent. In other words, that summation cannot represent a finite value. It is not summable. This is going to be one of the powerful tests to see whether a series is divergent, meaning not convergent. If you observe that terms in the series are not becoming close to 0 as n becomes larger and larger, immediately you can conclude that the corresponding series is not summable. Keeping this observation, let us go back to the question. Given an arithmetic progression a plus d, a plus 2d, etc., does the infinite series summation n equal to 1 to infinity a plus n minus 1 into d is convergent? Does this infinite series finally represent a number, real value? Note that for this series, nth term is a plus n minus 1 into d. Bear in mind that a and d are fixed finite real numbers, which are respectively first term and common difference of the AP. Once a and d is fixed, assuming d not equal to 0, we see that a plus n minus 1 into d becomes large when n becomes large in magnitude. If d is a positive number, then n minus 1 into d as n becomes large comes close to infinity. And if d is negative, n minus 1 into d when n becomes large comes close to minus infinity. Therefore, limit n tending to infinity a plus n minus 1 into d is plus infinity or minus infinity. What we observed is that nth term of the series that we are interested, namely arithmetic series, does not come close to 0 when n becomes large. Therefore, by the previous observation we had, the corresponding series is not summable. Therefore, summation a plus n minus 1 d n is equal to 1 to infinity is not convergent. As the nth term of the series does not come close to 0 when n becomes large, the corresponding series is not convergent. This is the case if d not equal to 0. And if d equal to 0, again, when d equal to 0, nth term of the infinite series we are interested reduces to a, which is fixed. Therefore, as n tending to infinity, the nth term does not become close to 0 when a is not 0. Limit n tending to infinity a, which is the nth term, is not 0 if a is not 0. What we conclude is that if the common difference is 0 and the first term is not 0, then the arithmetic progression is a and so on. Here the nth term is not coming close to 0. Therefore, the corresponding series a plus so on is not finite or it's not convergent. Only case left with is a equal to 0 and d equal to 0. In that case, the arithmetic progression is 0, 0, 0, so on. And the corresponding arithmetic series is 0 plus 0 plus so on, and which obviously is summable and the sum is 0. To conclude, except for the trivial case, the series corresponding to arithmetic progression, namely summation a plus n minus 1 into d, is not convergent. This is in contrast to geometric series. A geometric series, that is a series corresponding to a geometric progression, is convergent for some values of r. More precisely, for r lying between -1 and 1, both excluding, the geometric series is convergent. Let me stress on the observation we had. If summation n is equal to 1 to infinity is convergent, then that implies that an is close to 0 as n becomes large, written mathematically as limit n tending to infinity an is equal to 0. How do we utilize this result is by taking the contrapositive of the statement, namely, if you have a series summation n equal to 1 to infinity an, and if you could observe that an, the term, nth term, is not close to 0 as n becomes large, immediately we can conclude that the series is not convergent. However, if nth term becomes close to 0 as n becomes large, that does not guarantee anything about convergence of the infinite series summation n equal to 1 to infinity an. Keep in mind that if an becomes close to 0 as n grows arbitrarily large, then we cannot conclude that summation an is convergent. Very important remark. And to supplement this remark, let me give you an example. Let us consider the sequence 1, 1 by 2, 1 by 3, so on, 1 by n, so on. Corresponding series will be summation 1 by n, namely 1 plus 1 by 2 plus 1 by 3 plus etc. Recall that we proved the partial sum of this series has the property that s 2 power n is greater than or equal to 1 plus n by 2. 2 power nth partial sum is greater than or equal to 1 plus n by 2. So, the sequence of partial sum is not bounded it goes on increasing. Therefore, we cannot expect that the sequence of partial sum remains close to a fixed number. That is equivalent to say the series is not convergent. In other words, 1 plus 1 by 2 plus 1 by 3 plus etc. does not represent a finite real number. However, the nth term, namely 1 by n, becomes close to 0 as n becomes large enough. Sigma 1 by n is not convergent but 1 by n comes close to 0 as n tends to infinity. Thus, when you have a series summation an and when the nth term an does not come close to 0, conclusion is immediate, the series is not convergent. Whereas, if the nth term goes to 0, we cannot claim anything about the series. It will be more clear if I give one more example. Let me consider 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus etc. That is the sequence 1 by 2 power n minus 1 and the corresponding series summation n is equal to 1 to infinity 1 by 2 power n minus 1. It is not hard to see that this is a geometric series with first term as 1 and common ratio for the corresponding geometric progression is 1 by 2, which is less than 1. Therefore, by the observation we had earlier, this series is convergent, and in fact we have a formula for its sum, a by 1 minus r type. Now you observe that the nth term, namely 1 by 2 power n minus 1, becomes close to 0 as n becomes large enough. So, in this example, an tends to 0 as n tending to infinity and summation an is convergent. Whereas, in previous example, an tends to 0 as n tending to infinity, but summation an is not convergent. To sum up, if nth term of a series is not converging to 0, immediately conclude the series summation an is not convergent, and if it does converge to 0, we cannot conclude something about the corresponding series summation an. Don't bother too much about the technical details about the convergence, divergence of the series, but try to have a intuitive feeling of it. Having said that, let us move to some problems based on the concept we discussed so far. These problems should help you to remind you about the formulae that we developed in AP and GP, and it should supplement your theoretical understanding. First problem is this: sum of n terms of 2 AP are in the ratio 3n plus 8 by 7n plus 15. You are asked to find the ratio of their 12th term. The data is ratio of sum of n terms of 2 AP. Please recall that given an AP with first term A and common difference D, we do have a formula to find sum of n terms of that AP. Since we have to deal with 2 APs here, let us assume that first AP, arithmetic progression, has first term, let us call A1, and common difference D1. Then the AP will be A1, A1 plus D1, A1 plus 2D1, and so on. Let second AP has first term A2 and common difference D2. Then the second AP will look like A2, A2 plus D2, A2 plus 2D2, and so on. Nth term of first AP is first term plus n minus 1 into common difference. Nth term of second AP is first term plus n minus 1 times common difference D2. These formula we developed already. Now, what is given to us is ratio of sum of n terms of 2 AP. Recall that sum of first n terms of AP is given by the formula n by 2 times the first term plus n minus 1 into common difference. This is for sum of n terms of first AP. Similarly, sum of n terms of second AP will be n by 2 into first term plus n minus 1 into common difference. what is given to you is ratio of these two quantity n by 2 2a plus n minus 1 into d1 by n by 2 2a1 2a2 plus n minus 1 into d2 is given to be 3n plus 8 by 7n plus 15. Cancelling this n by 2, the given fact is 2a1 plus n minus 1 into d1 by 2a2 plus n minus 1 into d2 is equal to 3n plus 8 by 7n plus 15. Remember a1 and d1, the first term and common difference of first AP, a2 and d2, the first term and common difference of second AP are unknown. And this will give you, after simplification, only one equation. And there are many unknowns. So, we cannot expect it to be solved. However, let us see what is the question. Question is about finding ratio of 12th term. Remember, we have formula for nth term of first AP and nth term of second AP. Therefore, 12th term of first AP will be a1 plus 11 into d1 and 12th term of second AP will be a2 plus 11 into d2. We are asked to find the ratio of this a1 plus 11 into d1 by a2 plus 11 into d2. This is what we are asked. And what we have is 2a1 plus n minus 1 into d1 by 2a2 plus n minus 1 into d2 equal to 3n plus 8 by 7n plus 15. That is what we have. Finding the ratio a1 plus 11 ad by a2 plus 11 d2 is equivalent to finding 2a1 plus 22 d1 by 2a2 plus 22 d2. I multiplied numerator and denominator with 2. Now, see what we have. What we have is ratio of 2a1 plus n minus 1 into d1 with 2a2 plus n minus 1 into d2. In place of n minus 1, we need 22. That is, n is equal to 23. Therefore, the required ratio can be obtained by putting n equal to 23 in the given equation. Putting n equal to 23 in star. By star, I mean this equation. Putting n equal to 23, we have 2a1 plus 22 d1 by 2a2 plus 22 d2 is equal to 3 into 23 plus 8 by 7 into 23 plus 50. Now, simplifying this ratio, one may get the answer. I think the answer is 7 by 16. Please do the manipulation and confirm. We shall continue with more problems on AP and GP in the next class. Thank you.